So pleasure to be here. Good afternoon. I'll tell you a bit about some research that is at the intersection of machine learning and graphical models, methods. And I'll start by giving you a bit of a background where this fits in what you may have seen so far in the class or in the general field of learning theory. That's in fact my first slide. So that's a rough separation of the field. In learning, there's of course in between cases, semi-supervised, reinforcement, but in those two main camps, I'll remind you of the typical problems that people address. The first one, which is here classification. You're given a collection of data points, images of fruits, and a human being or someone has given you the labels for those images. So here, apples, bananas, and oranges. And then your goal is that train yourself on how to understand this category, these classes, come up with a method so that if I show you a new image, a new apple that you haven't seen yet, you would like to predict accurately that this is in fact an apple. So that's the supervised framework. And then what we'll discuss today is the unsupervised framework where you're not given the labels. You have a collection of images and you don't have access to what is what, and you would like to find some structure in that data set. So in this example, for example, reconstruct groups of similar images. Okay, so that's the goal, and the difference is that on the supervised level, there's a fairly unified framework, which is statistical learning theory, that allows to study approximation error, optimization error, and expressibility. In the unsupervised context, there isn't as much of a unified field. It's much more of a collection of different methods and approaches. In fact, if you went to Jan LeCun's talk about 2 weeks ago, this is the part that I referred to in his talk as the content of the cake. So the supervised learning was the icing, or the cherry. The icing was reinforcement, and the actual cake was the unsupervised, because there's much need to develop the theory, to develop the principles in this area. So I'll tell you a bit about one topic in unsupervised learning, community detection and graph clustering. And the idea is that, okay, you cannot start from nowhere. You cannot just group these images here and find some structure, some pattern, and say, okay, these are the apples, banana, etc. You cannot do that without having something to leverage on. So you need, in a sense, nothing is completely unsupervised in the word. So here, what we will have as the information that we will leverage is the fact that we will be able to compare data points, data images. And the idea is that these are like generic principles that will be reflected in what we'll discuss, is that, well, let's think of social interactions. There's a tendency to which a man is known by the company he keeps. This is like a famous proverb. But if I identify someone, and I tell you this person has worked with LeCun, Benjo, and blah, 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 and goes to these events, you can fairly quickly guess that he's probably a researcher in machine learning. Of course, it's not as simple as that. And this applies to other areas than just social interactions. So we will see the case of word embeddings. Often if I ask you to guess a word, and I tell you fruit, tree, Newton, and a few hints like that, you may at some point guess that this is an apple. So by the company the word has with other words, you can infer the meaning of the word. So we'll start from there, and this is the idea. So you're given a data set, and you will build a graph or a matrix. A graph is simply everything we will discuss is symmetrical. The interaction between ing and j and I is not going to depend on the order. You could have cases like that. We will only care about undirected graph. So a weighted graph is just a matrix that tells you how the item I and j are similar or related to each other. And if it's a simple graph, then that number is just 0 or 1. It means either there is an edge or there is not an edge. And if it's a weighted graph, there's a number which represents some measure of similarity, for example. So what could be this graph or these interactions? It could be friendship of people if you're in social network. It could be what's called a call graph. So we take people in this room and we connect with the number of times you call each other, let's say in a week or in a month. Internet traffic between machines. The next example is the one I briefly mentioned before. So how do you compare words? What you can do is you can say, let's take a corpus of words like Wikipedia, And let's count how many times word I and word J appear in the same phrase when we define a phrase to be a sequence of, let's say, 5 to 10 words or something like that. Okay, so that gives you a count, a number. And clearly words that are more interacting will appear with higher counts. So this gives you, again, a matrix or a weighted graph. Now, you can also have, the next example is similarity in pixel. You have an image, and you look at all the pixels in the image, and you build a graph between any pairs of pixels where you measure how similar those pixels are. So same color, same texture will be high scores. And then the last one is something that is called protein-to-protein interactions. You'd like to understand the structure of proteins. We cannot talk to proteins. So what you can do is measure who interacts with who, and this is also done in gene expression network. You try to see the interactions, and then you build this graph. And this is what you get out of this first phase. So here in the example of the images, you come up with a simple measure. If it has the same shape and the same color, it should get a high score. So like 2 oranges will get a high score. Let's say the score is between 0 and 1. But if you have the same shape but different color, you get an average score. If you have different shape and different colors, you get a low score. Okay, so now we have done that. This is the supervised kind of phase. And now we have access to our graph with some weights on the edges. Okay, the next step would be try to compress that graph. Try to represent it in a more succinct way than this big, huge matrix. And in particular, what we will focus on is the task of finding clusters, meaning in that graph, can we group the vertices into subsets that will be more closely related to each other with a lot of high edges, high weight edges inside, and also separate groups that are dissimilar. It's always important to address the two tasks, group similar vertices and separate dissimilar vertices. Because you can always solve one task, you can always group similar vertices safely by putting everybody in one cluster. I will be sure that I group everybody in the same, that are similar with that. But then I will not separate dissimilar vertices. I can also achieve the other purpose easily. If I want to separate all the dissimilar people, I can just put everybody in a cluster. And then I'm sure that I separated everybody that's dissimilar. But then I'm no longer grouping the similar vertices. So there's a tension between those two objectives, and we want to get both. That's why the problem is non-trivial. So I'll tell you a bit more about what I mean by compress and get data representation. And let's look maybe at the first example, which is a fairly old example. It's the experiment done by Ekman in the 50s. So what he did is he took a collection of subjects and he showed each people two colors, just a piece of paper with a color. So he had a collection of different colors, about 10. And he asked each individual to rank, to give a number between 0 and 1. I think it was 0, yeah. About how similar these two colors are. So I show you yellow and orange, and I ask you give me a score. You say 0.8. I show you green and yellow, or blue and yellow, and you may say 0.2. And this varies on people. Now he does that with many people, like an entire subject, and I think the number is here. Only 31, not that many, in fact. You could probably do much more today. And he averaged those numbers he obtained, and then he did something very simple. So now that's the collection, phase 1. Gather the interaction graph, so this matrix. Now he simply took the PCA, meaning the top 2 eigenvector that better. So that would be if you have a matrix M, which is symmetrical, and you take the top 2 eigenvector, which with the largest eigenvalue, this would be the best approximation of rank 2 of that matrix. So you try to get a matrix which is similar to the original one, but with only rank 2, with only 2 vectors. And then he simply plotted those 2 eigenvectors in the plane because he has, for each of the points, he has these 2 components corresponding to the first component in the eigenvector and the component in the second eigenvector. And this is what he obtained. He obtained a circle of each of these different colors. So each point here represents one of the colors he showed. And the interesting part here is that, as you can see, this is not too far from the actual circle of the colors, the actual wavelengths. And so this is the interesting aspect here, is that just out of these simple questions to people, which are clearly not correct, not accurate, but aggregating this and taking a rank 2 approximation of the data, it got a picture that is not too far from the wavelengths in the circle of colors. Okay, so let's look at another example. That's something that you may have heard. It came up much more recently in '08. I forgot if it's Science or Nature. And what the people did in this experiment is they took, again, a bunch of people, 3,192 people. And they, this time it's a bit more elaborate. They compared their genetic code. So I forgot the details on how they compared the genetic code, but they came up with a measure on how similar the genetic code of person I and J are. Okay, and then from there, they simply did something similar. So, okay, there's some transformation involved. It's maybe not as direct, but eventually they again do the PCA, take the top two most dominant components that explain this matrix of similarity of genes. And this is what they obtain if you plot them in the plane. So this is each point is one of the person. And as you can see, it's surprisingly close to the map of Europe. In fact, I think that there were about half of the people were located with only 400 kilometers of their origins, just from the genetic code. And I think if they have a comment in the paper that if you look into Switzerland, it was interesting because they found clusters of different groups, and that corresponding to the French, Italian, and German part. So after the colors you see here is that after getting that embedding of the points, then they solved their clustering problem. Then they tried to find groups of points that were more closely related. That's the clustering task. And if you don't want to do the clustering, but you only want to have the representation in 2D for other tasks, you can also use just those points. So what I will focus on is basically how do we get to these clusters, and how do we get even before the clusters to those useful representations. Okay, so that's the second example. That's the third and last example. This is the one I mentioned briefly before, the word embedding. So you have a matrix of co-occurrences. So let me repeat again. You take any pair of words. So there's like about 1 million of words or something around that. You count how many times word ing co-occur within 5 words in a corpus of words. And now there's some transformation involved, and then you take the, again, top eigenvalues. So you do a plot of the eigenvalues. And what you find is that these eigenvalues, they decay pretty quickly. So the dimension of the matrix of co-occurrences is of the order of 1 million. But if you look at the eigenvalues of that matrix, it kind of looks like this. So I'm plotting here the magnitude of the eigenvalue. They are large for some time, and then it drops. And then it's tiny for most of the components. And this is, if you look at the cutoff here, when it's significant, when it's not close to some low threshold, it's only about 300 when there's about 1 million dimension. So now that means you can use this eigenvector, these 300 eigenvector. Again, you stack them up, and that gives, if you read each row, that gives a representation of each word of dimension 300. Okay? So a word becomes a 300-dimensional vector. And what's interesting is that, again, not only you have the property that this approximates the counts that you observed, but this preserves also some semantic property in this case. And this is, for example, the experiment they do. There's multiple groups that do that. I didn't put a ref because I'm not sure where it started from. But basically, first of all, it satisfies this analogy property. If you take the vector, so this is a cartoon. This is 3 dimensions instead of 300. But if you take the vector for king and queen and you subtract them, then you get essentially the same vector as when you subtract man to woman. So what king is to queen is preserved in that Euclidean embedding. From man to woman. And if you do, for example, France minus Paris plus Rome, and you work with those vectors, Euclidean vector, then you get something which is close to Italy. And also you can do with that similarities, so you can cluster those vectors. They live in 300-dimensional. It's a bit bigger than 2-dimension, but you can again apply clustering algorithm, and then you can find groups of words that are similar. And you can do many more things. That's also you can do translations. Or, for example, you can classify documents. So you have, instead of using this on words, you can look at the similarity of 2 documents. You again have this big matrix. You do low-rank approximation, and then now you end up with a vector that represents a document, and then you can classify the documents that talk about sport, politics, etc. Okay, so now let's go into how do we get those clusters? And before the clusters, how do we get those representations of points? So this is a case we understand fairly well. If I give you a plot that looks like this, we are in a low dimension, Euclidean space, so R2, R3, R4, some low dimension. And I give you a bunch of points that are well separated, okay? Then that's a setup where we have many methods to separate those clouds. One algorithm that works fairly well on an example like this would be the k-means algorithm. So you've not seen k-means already, or do you know? Did you see k-means in the class? So that's an iterative algorithm. What you do is you start with 2 candidates for what the centers could be of your clouds. Let's say you know there's only 2 clouds. And then you say, okay, if these were my centers, then who would be blue, who would be red? And then that gives you a coloring of the nodes. And then you iterate. Now you say, okay, if these were blue, these were red, where would be the ideal centers of the blues and the red? That moves the centers to a new location. And then you keep going back and forth. Now we have new centers, we recolor the vertices, and we keep iterating. So it's an example of an EM algorithm. So it iterates and finds those clusters. And if you live in low dimension, it works pretty well if they're well separated. So that's what we would like to get to. So what I'm going to tell you next is that we don't have this nice picture to start from. That's what you do when you are happy with your representation and when you can already represent things in low dimension. Typically, we have data sets that are huge, millions of points, and we don't necessarily have something which is living in an Euclidean space. Things are living like gene similarities, have nothing to do with Euclidean vectors in some space. So here is an example which is harder. You have a graph, which is, this is a simple graph. It's just, let's say, who's friend with who. There's only 1,000 points in this image. But as you can see, there's nothing Euclidean in that. It's just a bunch of abstract 0-1 connection between n choose 2 people. So I built that graph in a special way. You will see that there is a structure in that graph. There's actually 5 groups. And the density inside the group is 20 times higher. That means if you look at the fraction of edges inside a group or across 2 groups is much higher. So as you can see, if you take a random partition of your 5 nodes, so now I'm just going to pick a uniformly at random partition. Now you can see there's many more edges between the groups than what we had in the previous picture. So the question is, you are given the original graph, and your task is to find, even let's say to simplify the discussion, someone tells you, a genie tells you there are only 5 clusters in that graph, just find them. Then you would have to reconstruct the first partition I showed. So if you don't have an algorithm, if you do it naively, you say, okay, let me look at all partitions of my 1,000 nodes in 5 groups. That's already more than the number of atoms in the universe, so you will not get this partition very soon. You'll only see this for like quite a bit of time. So you need to come up with methods and algorithms. That's where it has to be machine learning that approaches the problem and mathematics. So that's the goal. We want to partition now. I'll discuss the case of simple graph. You have this abstract object with either there's a 0 or a 1. That would be, let's say, the 1-bit quantization of any similarity measure. If we think we are similar, 1. If we are not, just 0. And of course, most of what I will say extends to cases where you don't have this 0-1 setup. You have just a number, but that's like an easier starting point, and there's enough difficulty already there. And these are examples. So this is a Facebook example, social networks with some communities related to either work or hobbies. This is the call graph, people calling each other with some small communities of people that are closely related. That's the PPI network, protein-to-protein interaction networks. That's the case of when I mentioned the example of similarity of pixels. Then if you find the clusters in this example, what you are trying to extract are the segment of the image. The segment are like this region, for example, here is a collection of pixels that will all be in the same cluster because they're all similar. And this will be a segment. So it's used in image segmentation. That's a gene co-expression network, and it's also used a lot in customer ratings and recommendation systems. So like Amazon may look at all the consumers it has. It will build a graph of how similar you and you are in terms of purchasing items. And then it will try to cluster the customers to better find similar. This is called customer segmentation, in fact. Similar customers so we can more accurately recommend or make advertisement. Okay, so that's probably why I also like this subject, is because it's pretty broad. These are all very different applications. Here you try to understand biological functioning, here image segmentation, and here recommendations. Oops. Okay, so I want to tell you, before we dive into the model, the block model, I want to tell you like maybe the mainstream way to approach the problem of how do you go from this abstract graph partitioning to a problem that looked like the slide I had before, that was the easy case, meaning this one. These are very different setup, right? Once you have given a graph, 0, 1 connections, and this is a bunch of points in the plane or in some low dimension. So is there a way to go from the graph to this Euclidean setup? And here is one way to do it, is you take what's called the graph Laplacian. So what is this? So from now on, I will start writing quite a bit on the board, so if it impedes your vision, you can see there. So the graph Laplacian is defined like this. D is a diagonal matrix with D1, D2, Dn, if it's an n by n graph. So I have G, which is n by n graph, so n graph, n vertices. A is the adjacency matrix. Aij is 1 if I is connected. If I and J are connected and 0 otherwise. Okay. And D is this diagonal matrix where you put 0 everywhere here. And di is the degree of the vertex I. So it's the summation of aij over all j. This is counting how many friends you have, the degree of the nodes. So now the Laplacian is defined as follows. You simply take this diagonal matrix of degrees and you subtract the adjacency matrix to it. So why is this a good operator? Because of this property. If you pick any vector x in Rn, so n again is the number of vertices, and you look at this quadratic form here, x transpose Lx, then what you are measuring is exactly how much is x varying on the edges of the graph. So let's verify this formula. X transpose Lx is this, x transpose D minus A. So we have the term x transpose Dx minus x transpose Ax. That's on the left side. Then here, if you expand the square, what you get is the summation Aij. Then we have xi square plus xj square minus 2xi xj. And this is over all I less than j. Okay. So now, if you look at, you distribute this Aij on each of these terms here, what you see is that there's going to be Aij times xi square, but I'm summing over, in fact, I can replace that sum by all I and j, and I put a half. Because if you do I less than j or all I and j, and then I half it, it's the same because the metrics are symmetric. So if I do this and I sum this over all j now first, then I'm going to pick up the degree. I'm going to pick up the degree of A, so that gives you degree di times xi square. And then when I sum over I, the second variable, then I'm exactly doing this term here, x transpose dx. This is the sum of di square, or di xi square. And then I do it again a second time, but I have a half that cancels out. And then I have twice the xi, xj, aij, which is this term here. This is an equality. And then I can rewrite it. See, what I did here is if you don't like the half, then you can rewrite it like I did. And this is the same because aij is 1 if there is an edge and 0 otherwise. Then this is the same as what I wrote here. So the sum of over all the edges of the graph, so that means Aij is 1, otherwise it's 0 and it cancels that term. And you look at how much xi and xj, if they are, how different they are using a square. So it's important because it will allow us to capture the following line here. So if you pick a subset S of vertices and you look at the vector x that corresponds to the indicator on that subset, normalize so that this is norm 1. So indicator means this vector is 1 if the vertex belongs to S and 0 otherwise. And then here I divide it by the root of the size of my set. So if I apply this vector to x transpose Lx, like this, then if I use this formula to evaluate what this is, what I get is that this will be 0 unless I pick two components that are not, that do not have the same value. In which case, this will be exactly 1 divided by the size of S because of the squaring. And this will happen for every edge such that I and j are not in the same set. You can see the picture here. Because if you have two vertices that are both in the set, then you have 0 contribution. But if you have one inside, one outside, then this will contribute to a 1 over S. So this is counting what's called the cut of S, the number of edges that are crossing from inside the set to outside the set. So that's the red formula here is why the Laplacian is nice. Because when you look at this x transpose Lx, then you are exactly measuring, for vectors of this form, then you are measuring how many edges are leaving my set and normalizing by the size of the set. And this is exactly something that preserves what I said at the beginning. When I said we want to separate vertices that are dissimilar, but we also want to group similar vertices, both of them are captured here because a low score, if you have an x that makes this score low, then it means there are few edges crossing your set. So that's good. That means we are separating groups by as few edges as we can. But we are also penalizing you by not trying to pick sets that are too small. Otherwise, you may end up having a single vertex in a cluster. It may only have one edge going out, but then you're normalizing by just one. Whereas if you put 1,000 nodes together, then you're normalizing by 1,000. So you're trying to, making that ratio small is trying to make both the number of edges leaving small, but also the groups having critical mass. So now the problem is that, in theory, if you could solve what is the best set S so that you get the lowest value for that ratio, that would be like great. It would give you the best separation of your graph into a subset S and its complement so that you have a sparse cut. But you cannot do that efficiently because this is a problem that is an integral optimization problem. This is a hard constraint. You're asking for your vector x to be taking only 2 possible values. And for that, we don't know how to solve this efficiently in large dimension. But what we can do is say, well, this is just a norm 1 vector. It's a vector that has norm 1. Why don't we forget that it has to take only 2 possible values and use the following relaxation? And we're just going to say that the norm of x is 1. Okay? Instead of saying that it has to take only 2 values. So of course now we no longer have exactly a formula like that, but the hope is that if we look at a vector x that has a small ratio here, and then we do a rounding, and then we say, okay, whoever is positive, I say group 1, whoever is negative, I say group 2, maybe this will be not too far from a solution from here. Or there's a different way to do the rounding, but that's the intuition. Now the good news is that if you forget about this integral constraint and go to an x which is a real valued vector, now you know what problem this is. If I ask you find the minimum of this under this Euclidean constraint, what is this? What is the vector that minimizes x transpose a matrix X when X has norm 1? L is symmetrical, so L it has an eigenvalue decomposition, and if you try to find the vector with least inner product here, it's exactly going to be the eigenvector of L with smallest eigenvalue. So that's I'm giving you just the insight here. You don't have to follow all the steps, but this is the basis behind the spectral clustering algorithm. What it's going to do, so if you want 2 group, you're just going to pick k is equal to 2, but if you want k group, you ask for k eigenvectors. So you pick the lowest eigenvectors corresponding to the lowest eigenvalue of this matrix L. Let's say you could pick only 2, that's what I did here. And then you look at this problem, which is exactly the setup that we like. Now we are back to a problem where we have endpoints that only live in dimension 2, if I pick k is equal to 2. And this is the spectral embedding. This is what this eigenvector bring to you. And now we can apply the methods that we are, like k-means, for example, or methods that exploit the fact that we are living in a Euclidean space, meaning we can use distances in our product, projections, and things like that. And k-means, for example, if those clouds are well separated, the k-means will do well. So that's how you go from a problem which is in an abstract graph where there's no geometry, no Euclidean setup, how with a Laplacian and with this eigenvalue decomposition and picking up the top eigenvector, a bit like we had in all the first examples, how you end up again in a problem like this, and where you go with now k-means and algorithm like this. So this is like one of the most spread out algorithm for clustering. It works well in some cases, but not always. I'll show you example where it fails. And I'll just summarize what we've seen so far. So what's happening is there seems to be a general recipe in some of these unsupervised problems we've seen, which is you get some data set. You try to find a good interaction operator. So you measure similarity of genes, or just is someone friend or not with someone else. Then you may use some transformation, and you take the top eigenvectors. So the transformation was the d minus a in the case of graph clustering. Then you take those top eigenvectors that only have either the lowest or largest eigenvalues. It depends what the problem is. It's always pretty clear, like if in the Laplacian context, because you do d minus a, then you don't want to pick the lowest. You want to pick the lowest because I'm doing minus a. If I were to work directly with the A matrix, then I would like to pick the largest eigenvalue. There's never ambiguity in the applications. One gives you nothing interesting, the other one is what you want. So you find those top eigenvectors, and then this gives you some representation of the point, and then you can resolve the clustering task using a Euclidean algorithm like k-means. Okay, so these do not work exactly like I showed you in the slides. I've put quite a few things under the rug. So if that's the example of the failure of the Laplacian, so here is a graph where I generated the graph with the clusters as follows. There's 10,000 vertices. I put edges inside each cluster independently between any pair of vertices with probability a divided by n, where a is 2.2. And I've put edges across for any two vertices that are in different clusters independently with probability b by n, where b is 0.07. So there's like much more. There's like about, I don't know, what is it, about 50 times more connection inside the group, inside the clusters and across. So there are significant clusters in this graph. But if you apply the method that I described to you 2 slides ago, this is what spectral clustering picks. This is an example of a graph where it will put everybody here in one cluster, and the rest of the graph is the second cluster. So it's finding a cut which is very sparse. It's a single edge crossing. And there's still enough critical mass not to make this guy insignificant. And this is beating the cut that the middle part has. And so this is not what you would like to find. You would like to cut in the middle. And that's an example where it doesn't. In general, you have to basically do quite a few things to make spectral clustering or methods work. Like there's other tricks that I will discuss a bit, normalize, random walk Laplacian. Or you can, if you use PCA, like in the first 2 examples for the genes and for the color example, you have to be careful to do centering, normalization. Sometimes you do thresholding so that you don't pick eigenvectors that are, for example, in the case of word embeddings, if you don't do something with the word D, if you don't do something with this word, then your embedding will put all of these words with a single vector. So you basically have to do some processing to regularize a bit your data. And this sometimes can be very subtle. So for word embeddings, there's a whole industry on using the log PMI matrix, the root PMI, and also using neural nets to extract those embeddings. And this is the part where basically at the moment it's a bit more of an art than a science. And the game is how do we build those operators out of data with some principles. Okay, so that's what we want to find. How do we design reliable operators, and how do we measure reliability? And if we want to talk about notion of optimality or what's good or bad, of course we need to come up with a model. Otherwise we cannot. And for community detection, the big question are going to be this one. How do you know that there are really communities in your data set? Or are you extracting some artifacts that your algorithm brings? How much can you reconstruct the communities? Can you get them fully or just partially? Are there some limits to how much you can extract communities? And of course, how well are the algorithms we have? Are there new algorithms, etc.? Okay, so as I said, we need models to start doing some math and being able to quantify what we want by success or failure. And here is the model. That's the second phrase in the title of the class. So the stochastic block model is a canonical model that has been used for the problem of community detection. And it works like this. So this is what I call the vanilla block model. You just have your n vertices that are split into two groups that are uniformly randomly split of n over 2 for each group. So that's the case of a balanced partition. And now you put edges with probability A independently inside each group. Okay, so you look at the vertex here. You flip a coin which has probability A, let's say 0.2 of being 1, and you put an edge if this came out 1, and otherwise you don't. Then you do this across any pair of nodes with probability B independently. So it's exactly the example I had before. Now that's the vanilla block model because you can define this in a much more general context where instead of having two groups, you have k groups. And in this case, you use the parameters n, p, w. So the n is the number of vertices, in this image 1,000. P now is going to be a vector which has 5 components in this example because I use k is equal to 5 for 5 groups. So the dimension of P is the number of cluster. And Pi, the ith component of P, is the relative size of cluster I. So there's different ways to define the partition. Either you do it by exactly asking your group to have like group J should have n times Pj nodes, okay? And then you look for a partition uniformly at random that preserves those size. Or you take every node and you color it independently with that distribution. Okay, so I have this die that is a balance, this coin that has 5 sides equally likely, and I say, okay, you're blue, red, yellow, etc. And by the law of large number, by concentration, the size of the groups will be, when you normalize the size by n, you will tend to these 5 values that you start with. Whatever I will say in this class is the same if you do the model where you exactly split equally with the size you want, or whether you do this soft coloring independently to each node, because as n tends to infinity, the two models become equivalent by the law of large number. Okay, so that's the second parameter P. P is the relative size of the communities. Then there is a third parameter W, which is this matrix. So it's a k by k matrix. And Wij tells you with what probability a node that has color I and a node that has color J connect. Okay, so in this example, I took a special case. I took the case where everybody inside the group has the same probability of connecting. That's why the clusters look the same. And everybody across any pair of group has the same probability B of connecting. And I took A is 1 over 50, B is 1 over 1,000. But in principle, you could have something which is with different shape, with different size, with different densities. And that would be a more general block model. So this is what I call the symmetric block model when I use the same value for P and the same value on the diagonal and outside. Then I would say the block model is symmetrical. And I think I will only discuss symmetrical models here to simplify. Okay, so I don't think you need the formal definition. Any questions on the model? Maybe it's important that you have the model right. If you want me to clarify something. So the game is going to be, we generate a graph like this, we erase the color, we scramble everything, I give you the graph, and your goal is to go back to that picture. And now we're going to discuss what does it mean to go back? How do we measure going back? So let's define the agreement. The agreement is simply, forget about the pi now for a moment. This is how many components. So I'm talking about the agreement between x and y. There are two vectors of dimension n. K is just a notation. K means the K color. So K is the set 1, 2, K. So this is a vector of dimension n that takes value for each component between 1, 2, 3, 4, 5 to K. So it's a coloring of your n nodes. So the question is, you count how many times is the X is one coloring, Y is another one. How many times do they agree? How many times is red, red, yellow, yellow, etc. And then you normalize by n, the number of vertices. So that's a fraction of correctly labeled nodes. Now the problem is that if I give you the example I had before with the two groups, for example, and let's say you come up with a reconstruction which is perfect, except that you call the blue guys red and the red guys blue, then of course that's a perfect clustering. You found the right partition. You just name the nodes differently. So this we should be as good as finding. There's no meaning to the colors. The colors are here to help us define things, but what we want is the partition. So that's why I have this pi here. This pi is allowing you to, you take your reconstruction, let's say X is what you look for and Y is what you reconstructed. So you measure the agreement. For any relabeling of the colors, you try first your partition when you call this blue, red, yellow, and then you try when you call this yellow, blue, red, etc. This is the symmetry group over K color. Okay, so that's the agreement notion. And now we're going to say that an agreement of alpha, so this is a number between 0 and 1, right? Because you cannot, at most, everybody is right. That gives you an agreement of 1, since I normalized. Or at worst case, perhaps you could get 0. So this is achieved in an SBM model if there is an estimator, some algorithm that takes the graph and outputs the colors on the vertices just from the graph, such that if you measure this agreement, then it is alpha with high probability. So that's little o n of 1 means it's something that goes to 0 as n goes to infinity. So we are only going to ask to succeed as the number of vertices grows large. But we want to be succeeding with probability that tends to 1. And this is the agreement alpha that we're targeting. So now there's different problems that people have looked at. There's the first case is, so we say that alpha star, this is a placeholder for the word I'm going to put here. So blah recovery is solved if you can get an agreement of alpha, where alpha is, this is the corresponding alpha. So we talk about exact recovery if you get a perfect agreement of 1. Means you have labeled everybody perfectly. That's the maximal agreement you can have. Then we talk about almost exact recovery if you can get everybody but a vanishing fraction of nodes. So little o of, this is a notation for something that goes to 0, as I said before, as n goes to infinity. So that means you have a few guys that are mislabeled, but in the limit they vanish. Then there is the regime of, let's look at the last one, weak recovery. So weak recovery, and here that's why I put in parentheses for SSBM. Let's assume for a moment that we're in the symmetric block model. So in the symmetric block model, you can convince yourself that the worst score you can have for the agreement is 1 over the number of groups. For example, if you flip a coin for every node, you just say, I'm going to forget about the graph. I just flip my coin to color U. Then I'm just by pure luck, I will get 1 over K agreement out of this proportion. So this is like the worst case scenario that you try to beat. So weak recovery is going to say, can we do better on this random guessing? Can we use the graph to at least get omega of 1 means something which is bounded away from 0? That's just the notation for some positive epsilon, some number that doesn't vanish. So can we get, let's say, 51%? That's what we want in the case of two groups. 50% is essentially what you get with random guessing without looking at the graph. But now I ask you, I want in the limit to get 51%. That's the first time you extract some meaningful clusters. It could be, it's very poor, 51%, but it's detecting something, it's catching something. So that's weak recovery, and then if you anything in between weak and almost exact or exact is going to be partial recovery, whatever, 70% could be your target. Okay, so that's break time, and then after the break we will discuss the regimes where we should study this problem.